150 million kilometers from the Sun, inside the very solar system it governs with light and gravity, you would be freezing. That seems impossible when you consider what lies right there, a star with a surface temperature of approximately 5,500 degrees Celsius, whose outer corona, the most distant layer of its atmosphere, regularly exceeds 1 million degrees. The Sun radiates energy equivalent to 384 septillion watts per second, a number so colossal that if you tried to write it out in full, it would fill an entire line with nothing but zeros. To grasp what that truly means, consider this: all the electrical energy consumed by all of humanity across its entire recorded history, from the invention of the light bulb to this very moment, amounts to less than a fraction of a second of the Sun's total energy output. And yet, the space surrounding this star of immeasurable power is approximately negative 270 degrees Celsius, just 3 degrees above absolute zero, the lowest limit that physics allows to exist anywhere in the universe. How is that possible? How can you exist within the system of a star that unleashes unimaginable energy at every single instant, and still find yourself enveloped in an environment that flirts with the coldest temperature reality will permit? The first answer most people reach for is simple: space is cold because it is far from the Sun. But wait, 150 million kilometers is not far, not in any cosmic sense. It is the very distance that solar radiation travels to reach Earth, to illuminate the oceans, sustain photosynthesis, and warm your skin on a summer afternoon. Mercury, a mere 58 million kilometers from the Sun, reaches temperatures above 430 degrees Celsius on its sun-facing side, hot enough to melt lead. Mars, at 228 million kilometers, experiences summer temperatures of up to 20 degrees above zero at its equator. Yet the space between these planets, that same space that solar radiation relentlessly crosses in every direction, remains perpetually close to absolute zero. Temperature does not fall gradually with distance the way you would expect from a conventional heat source. Interstellar space, within the solar system itself, saturated with solar energy at all times, stays anchored near the coldest extreme. Distance is not the explanation. Something far more fundamental is at work, and understanding it will forever change the way you think about heat, energy, and the universe. The confusion begins with an assumption so deeply embedded in everyday experience that it is almost never questioned. The idea that energy from a heat source naturally warms the surrounding environment. When you light a fireplace, it warms not just the stone directly in front of it, but every cubic inch of air in the room. When sunlight beats down on asphalt, the heat gradually spreads through the air above, warming the entire neighborhood. It seems obvious the same should happen in space. The Sun radiates energy. That energy spreads across the solar system, and the surrounding environment should warm progressively. But that expectation depends on something specific. That earthly experience takes for granted the presence of enough matter to receive that energy and carry it from one point to another. It depends on an environment that can actually be heated. And space, for the most part, is an absence of matter so profound it has no equivalent in any experience you have ever had. Interstellar space contains, on average, less than 1 particle per cubic centimeter, even in its densest regions, in the spaces between stars. That number drops to something close to a single atom per entire cubic meter. For a real sense of scale, the air you are breathing at this very moment contains approximately 27 quintillion molecules per cubic centimeter. The difference between the air that sustains your life and the interstellar vacuum is incomparably greater than the difference between all the oceans of Earth and a single drop of water, with the oceans representing the air and the drop representing the void. In a vacuum like that, there is no environment for the Sun to heat. The Sun emits, the radiation travels. But between the source and any object it eventually strikes, there lies a void so deep that two of the three mechanisms defining how heat moves on Earth simply vanish. And without those mechanisms, the thermal equation of the universe operates in a way completely unlike anything you had come to expect from living inside an atmosphere. That is the essence of the paradox. It is not that the sun is weak. It is that heat, in the precise physical sense of the word, cannot exist in space the same way it exists in air. Energy exists in space in abundance, traveling in every direction at the speed of light at every moment. But energy in motion is not the same as heat being transferred. For the temperature of an environment to change, for heat to pass from a source into the surrounding space, transfer mechanisms must be actively at work. And space, by its very nature as a near-perfect vacuum, disables most of those mechanisms so completely that the result, an environment near absolute zero inside the system of an immensely powerful star, ceases to seem paradoxical and begins to seem inevitable once you understand what heat truly is and how it truly moves. Heat, in its most precise physical definition, is neither a substance nor a static property. It is a process. It is energy being transferred from a hotter object to a cooler one through specific mechanisms. And the concept only holds meaning when those mechanisms are active. Temperature, in turn, is the measure of the average kinetic energy of the particles within a substance. The faster the molecules of an object move and vibrate, the higher its temperature. In a solid, that motion takes the form of molecules vibrating around fixed positions within the material's structure. In a gas, it is the speed at which free molecules ricochet in every direction. In a plasma, like the interior of the sun, it is the frenetic energy of separated electrons and ions colliding continuously at colossal velocities. Every degree of temperature represents a real and measurable change in the average speed of that motion. An object at 100 degrees Celsius has molecules moving significantly faster than an object at 50 degrees. And that is why the hotter object transfers energy to the cooler one when they come into contact. The more agitated molecules push the slower ones, driving up their speed. That is heat in action at its most fundamental level. No magic, no mystery, just molecular agitation being shared. The mechanisms by which this process unfolds are three, and each one demands specific conditions to operate. The first is conduction, medium, the process by which heat travels through direct collisions between adjacent particles. When you leave a metal spoon inside a cup of hot tea and then pick it up by the handle, you feel the metal warming rapidly, even though the flame never touched that point. What is happening is a molecular chain reaction. The molecules of the hot tea collide with those of the spoon at the submerged end, transferring part of their energy. Those more agitated molecules collide with their neighbors along the metal, which collide with the next, propagating the agitation all the way to the handle in your hand. Metals conduct heat well because they possess free electrons that carry energy efficiently throughout their entire structure. Wood conducts it poorly, owing to its porous and irregular molecular structure. Air conducts it moderately, its sparse molecules colliding far less frequently. And the vacuum conducts absolutely nothing, not because it is a poor conductor, but because there are no particles there to collide. In the vacuum, conduction is a fundamental physical impossibility, not an engineering limitation. The second mechanism is convection, stars the transfer of heat through the physical movement of a fluid. When air near a radiator is heated, its molecules move faster, the gas expands, becomes less dense, and rises. Cooler, denser air descends to fill the space left behind. This creates circular currents that continuously distribute heat throughout the environment, like a conveyor belt carrying energy from one point to another without interruption. It is convection that spreads the warmth of a fireplace across an entire room, that drives the winds of Earth's atmosphere by carrying heat from the tropics toward the poles, that causes water in a pot to boil progressively from the bottom upward rather than only at the base. Convection is the great thermal equalizer of fluids, and it demands, absolutely, the existence of a fluid to function. Liquid or gas, it makes no difference, but something must be present to generate the currents. In the vacuum of space, there is no fluid. Convection simply cannot exist. With two of the three mechanisms eliminated by the vacuum, only electromagnetic radiation remains, and it is fundamentally different from the other two because it requires no material medium to propagate. Radiation travels in the form of electromagnetic waves. Visible light, infrared, ultraviolet, radio waves, X-rays. These waves cross the vacuum with the same speed and efficiency with which they would cross any material medium because they need nothing to move through. They are electric and magnetic fields oscillating through space, self-sustaining, independent of any intervening substance. Every object with a temperature above absolute zero constantly emits electromagnetic radiation, and the type and quantity of that emission depend directly on the object's temperature. The Sun, at 5,500 degrees, emits primarily visible light and ultraviolet radiation. A human being, at 37 degrees, emits primarily infrared radiation. That is why night vision cameras can detect people in the dark without any visible light source. Radiation is the only channel of heat transfer that the vacuum cannot block, and it travels across the entire solar system with no significant loss along the way. But here lies the distinction that explains the entire paradox. Radiation heats objects, not the space between them. When sunlight crosses the 150 million kilometers between the Sun and the Earth, it does not heat the vacuum it passes through. It simply travels through it, encountering nothing to warm. The space it crosses remains near absolute zero, even as the radiation blazes through it at the speed of light. Only when that radiation meets something capable of absorbing it, an asteroid, the surface of the moon, your skin, a solar panel, only then is it converted into heat within that specific object. The space between objects is merely the path, not the destination. And that is why the Sun can be the most powerful star in the neighborhood while simultaneously coexisting with space that remains at the -270 degrees Celsius all around it. The physics of radiation in a vacuum simply permits nothing else. Heat does not exist in space. It exists within the objects that occupy space, and between them, the cosmos endures in the thermal silence that defines 99% of the observable universe. When an astronaut steps outside a space station to perform work on its exterior surface, they confront a thermal reality that has no equivalent anywhere on Earth. With the suit facing directly toward the Sun, the outer surface can reach approximately 120 degrees Celsius, bana, hot enough to cook an egg on direct contact with the material. With that same suit turned toward deep space, just a few centimeters away, the temperature can plunge to below -100 degrees Celsius. The thermal difference between two sides of the same object, separated by mere millimeters of material, can exceed 220 degrees. And that difference holds indefinitely, because in the vacuum, there is no air to redistribute heat between them. On Earth, if you heat one side of a metal plate with a flame while the other side is exposed to cold air, the temperature difference between the two sides will never remain very large for very long. The surrounding air conducts and circulates, gradually smoothing the gradient. In space, each surface exists in its own isolated thermal regime, cut off from any equalization by the absolute vacuum. Modern spacesuits are arguably the most sophisticated pieces of portable engineering ever created by humankind. And the vast majority of that sophistication exists to solve problems that arise solely because, in space, heat cannot move the way it does on Earth. The suit must reflect enough solar radiation to prevent the sun-facing side from overheating the astronaut within. But at the same time, it must ensure that the metabolic heat the astronaut produces simply by being alive, breathing, moving, working, can somehow escape. On Earth, that body heat is naturally dissipated into the surrounding air through convection. In space, with no air, that heat builds up inside the suit with nowhere to go, creating a thermal trap that can turn fatal within hours without active management. The solution is a liquid water circulation system embedded in a layer of the suit in direct contact with the astronaut's skin, absorbing body heat and carrying it to a sublimator and cytomorphin, a device that releases tiny quantities of water vapor directly into the vacuum, carrying the heat away with it. It is the only functional means of dissipating heat when convection does not exist. The surface of the Moon is the most accessible laboratory we have for observing this physics without the complications of an atmosphere. Under direct sunlight, the lunar surface temperature reaches approximately 127 degrees Celsius. In the permanent shadow of polar craters, that temperature plunges to around -173 degrees Celsius. This range of 300 degrees exists across the same rocky surface because the Moon has no atmosphere to redistribute heat through convection and conduction. The transition between the sunlit zone and the shadowed zone is nothing like the gentle gradient you feel on Earth when stepping from sunlight into the shadow of a building. On the Moon, the thermal boundary between sunlight and shadow can represent a difference of more than 300 degrees, occurring across a distance of just a few centimeters. Apollo mission engineers had to meticulously calculate the orientation of the lunar modules to ensure that the cycles of expansion and contraction in metallic materials, evangelion, induced by temperature variations across the lunar day of 29 Earth days, diata, would not generate mechanical stresses severe enough to compromise critical structures. The lunar environment was not a threat merely because of extreme heat or extreme cold. It was a threat because of the brutal, relentless alternation between the two. Artificial satellites in Earth orbit face an accelerated version of that same challenge. In low orbit, a satellite completes one full revolution around the Earth every 90 minutes, crossing the planet's shadow cone 16 times per day. With each pass through the shadow, the temperature of uncontrolled surfaces plunges by tens or hundreds of degrees within minutes as the satellite stops receiving solar radiation and begins radiating its own heat into the surrounding void. When it re-emerges into sunlight, the temperature climbs just as rapidly. Over a 15-year operational lifespan in orbit, that amounts to roughly 84,000 thermal cycles, each one expanding and contracting the satellite's materials. At cumulative scale, that process can cause structural fatigue, electrical disconnections, and failures in critical components. Every bolt, every junction, every circuit board on a satellite is designed not merely to function at a specific temperature, but to survive that staggering number of repeated thermal stress cycles. An engineering requirement that exists nowhere else in any technological application on Earth. The James Webb Space Telescope, launched in late 2021, represents the absolute frontier of what is possible in space thermal engineering. To detect the infrared light of galaxies more than 13 billion light-years away, its scientific instruments must operate at approximately -233 degrees Celsius because any residual heat in the detectors would generate their own infrared emission, completely drowning out the extraordinarily faint signals from the most distant objects in the observable universe. The solution was a sun shield the size of a tennis court, composed of 5 layers of a specialized film separated by minimal vacuum gaps, capable of blocking more than 99.9% of incoming solar radiation. The side of the telescope facing the sun reaches 85 degrees Celsius. The side facing deep space cools naturally to -233 degrees purely through the emission of infrared radiation into the surrounding void, with no active refrigeration system whatsoever, nothing but the physics of radiation in a vacuum, applied with surgical precision, the very same principle that would kill an unprotected astronaut within minutes. And it is that same force that allows the James Webb to peer back at the light born in the first moments after the universe itself began. If temperature measures the agitation of particles, and space contains almost no particles at all, what does it even mean to say that space has a temperature? That is not a rhetorical question. It has a precise and measurable answer. And that answer is one of the most extraordinary discoveries in the science of the 20th century. Intergalactic space has a temperature of approximately 2.7 Kelvin, equivalent to negative 270.45 degrees Celsius. But this is not the temperature of any gas, any dust, or any known form of matter. It is the temperature of a radiation field that permeates every corner of the observable universe with near-perfect uniformity in every direction. A faint, frozen whisper of microwaves, so cold and so feeble, it is completely invisible to the human eye. Yet, it is passing through your body at this very moment, streaming in from every direction in the cosmos with equal intensity. To understand where this radiation field came from and why it holds exactly that temperature, you must journey back 13.8 billion years. To the moment when the entire universe was compressed into a density and temperature that has no equivalent in any observable phenomenon today. In the first instance, after the Big Bang, the universe was a plasma of energy and matter, so ferociously compressed that temperatures reached into the trillions of degrees, far too extreme for any structure to exist. There were no atoms, because any electron attempting to bind to a proton was instantly torn away by the violence of the collisions surrounding it. There was no light traveling freely, because the universe was so dense that any photon could only travel a microscopic distance before being absorbed and re-emitted by another particle. It was an opaque, uniform, incandescent cauldron, endlessly expanding. As the universe expanded, it cooled, just as any gas loses heat when it expands, and after approximately 380,000 years, the temperature finally dropped below a critical threshold near 3000 Kelvin. At that moment, electrons were able, for the very first time, to combine with protons without being instantly torn apart, forming the first stable atoms of hydrogen. And with the birth of those first atoms, the universe became transparent to light for the first time in its existence. All the radiation that had filled that young, opaque universe was suddenly set free, traveling in every direction simultaneously in a single, all-encompassing emission from every point of visible space. That light did not vanish. It was not absorbed. It has been traveling ever since that moment, 13.8 billion years ago, and it is still in transit right now. But as the universe continued to expand through the eras that followed, space itself stretched, and with it, the wavelengths of that radiation stretched as well, growing progressively longer and less energetic. What was scorching infrared radiation in the young universe is today microwave radiation, with wavelengths of approximately 1 millimeter. Corresponding to the spectrum, a perfect black body would emit at exactly 2.7 Kelvin. This field of radiation is known as the cosmic microwave background. It fills every corner of observable space with such breathtaking uniformity that, if you could perceive it directly with your eyes, the entire sky would glow before you with equal intensity in every direction, with no difference whatsoever between north, south, zenith, or horizon. The observational discovery of this field in 1965 was at once accidental and revolutionary. Two engineers calibrating a highly sensitive radio antenna encountered a persistent background noise that refused to disappear, no matter which direction the antenna was pointed. That noise, initially blamed on equipment contamination, including the presence of pigeons that had nested inside the antenna and left material on its inner walls, was, in fact, the thermal echo of the Big Bang itself, arriving uniformly from every point in the sky. The confirmation of this radiation field provided the most direct observational evidence that the universe was born in a state of extreme heat and density, transforming the Big Bang theory definitively from hypothesis into scientific consensus. In the decades that followed, satellites specially designed to map this field with ever-increasing precision revealed that it is not entirely uniform. There are minuscule temperature variations, on the order of hundredths of thousandths of a degree, representing fluctuations in the density of the primordial universe during its first 380,000 years. These nearly imperceptible variations are the fossil imprints of the seeds from which the first stars eventually grew, the first concentrations of matter and the first galaxies. The complete thermal map of the sky, measured with precision down to fractions of a thousandth of a degree in every possible direction, is literally a portrait of the universe when it was less than 400,000 years old, the oldest photograph that exists. Captured not with visible light, but with microwaves, not of specific objects, but of the entire cosmos, all at once. And what that map reveals is that the 2.7 Kelvin, cold permeating space, is not the absence of heat. It is a presence, the residual warmth of the hottest moment the universe has ever known, cooled across billions of years of expansion to the very edge of absolute zero, yet still here, still measurable, still traveling in every direction simultaneously. The cold of space is the oldest signal in the universe, cutting through the frozen vacuum of the cosmos and passing through you right now, carrying within it the record of the instant when everything began to exist. The knowledge of how heat behaves in a vacuum was never confined to physics laboratories or spacecraft engineering manuals. It is in your hands right now if you happen to have a thermos nearby. The thermos, that everyday object that keeps coffee hot for hours and ice water cold for an entire day, works by exactly the same principle that makes space so cold. It uses the vacuum as an insulator. Between the two walls of glass or metal in a well-designed thermos, there exists a space from which the air has been almost completely removed. With no air between the walls, conduction and convection cannot transfer heat from inside to outside, or from outside to in, to block the only remaining form of heat transfer as well, radiation. The inner walls are coated with a highly reflective surface, usually silver or polished aluminum, that bounces back the vast majority of infrared radiation emitted by the contents. The result is a vessel that holds its contents at a stable temperature for hours, governed by the very same principles that rule the space between planets. Every time you reach for a thermos, you are harnessing the physics of the cosmos for your everyday comfort, holding the engineering of the vacuum in the palm of your hand. That same logic, guiding the design of spacesuits and telescopes, is actively shaping the way we construct buildings in the 21st century. Vacuum insulation panels, chambers of vacuum wrapped in reflective barriers, exactly like a thermos scaled to architectural proportions, are being built into the walls of high-efficiency buildings across the world. A wall just 10 centimeters thick with vacuum insulation can achieve the same thermal performance as a concrete wall 1 meter thick, because by eliminating the two mechanisms of heat transfer that depend on matter, it forces any energy flow through the only remaining pathway, radiation, and then reflects that radiation back. The cryogenics industry, responsible for storing gases at extreme low temperatures, liquid nitrogen at -196 degrees, liquid helium at -269 degrees, depends entirely on this same physics to sustain temperatures that would otherwise be impossible to maintain. Wherever humanity needs to create and hold a significant temperature difference between an interior and an exterior, the physics of space is there, serving as an engineering tool. Beyond the practical applications, the behavior of heat in a vacuum carries implications that touch directly on the most fundamental question contemporary science pursues. Where else in the universe can life exist? Life as we know it requires liquid water, and liquid water is only stable within a temperature range between 0 and 100 degrees Celsius. But in space, without an atmosphere to redistribute heat through convection and conduction, keeping a planetary surface within that narrow temperature band is extraordinarily difficult. The Moon demonstrates this in absolute terms. With no atmosphere, its surface swings between positive 127 degrees and negative 173 degrees, a range of 300 degrees across a single surface, making the stable existence of liquid water completely impossible. Earth transformed that problem entirely because it holds enough mass to retain a dense atmosphere, and that atmosphere functions as both a blanket and a heat distribution system simultaneously. The oceans store enormous quantities of thermal energy and carry it across hemispheres in vast, sweeping currents. The result is a planet where the temperature range across any annual cycle in any inhabited location rarely exceeds 60 degrees, extraordinarily stable by the standards of the universe. What this tells us about the search for life is profound. A planet at the right distance from a star to have liquid water on its surface is not by itself enough. It needs a sufficiently dense atmosphere to actively redistribute heat, transforming the pure radiation regime of space into a thermally homogeneous environment, stable enough for complex molecules to exist and self-organize across billions of years. Without that atmospheric shield, even a planet in the perfect habitable zone would resemble the Moon, one side scorched beneath its star, the other frozen in the vacuum, with a lethal temperature boundary dividing them. Life, at least as we know it, is not simply a matter of average temperature. It is a matter of a planet's capacity to soften the thermal brutality of existing in a universe where vacuum dominates, and two of the three mechanisms of heat transfer simply do not function. It is a matter of atmosphere as planetary technology, built from gravity and chemistry, to tame the physics of space and carve out a pocket of exception in a cosmos that operates by entirely different rules. And here is the most dizzying part of this entire story. The air you are breathing right now, the temperature you feel against your skin, the fact that both sides of your face sit at roughly 36 degrees at this very moment, rather than one side at positive 120 and the other at negative 100. All of it exists only because you are inside a bubble of convection and conduction, sustained by a planet with enough gravity to hold an atmosphere positioned correctly for that atmosphere to remain stable, and at just the right distance from a star for temperatures to be compatible with liquid water. You are living inside an exception. The universe, in its immensity, is dominated by vacuum and radiation, set by surfaces that alternately freeze and superheat with nothing to soften the process, and by a microwave background sitting at 2.7 Kelvin, the cooled echo of the beginning of everything. The cold of space is not a curiosity. It is the default state of the cosmos. The warmth you feel right now, the thermal equilibrium that sustains your existence, is the result of a planet that managed to create conditions in which the physics of heat operates differently than it does everywhere else in the observable universe. Which of these revelations do you find most fascinating? That space is cold for reasons so precise and so identifiable that the universe still carries the thermal echo of its own birth in every single centimeter of the vacuum, or that the very same principle that makes interstellar space so bitterly cold is precisely what keeps your coffee hot inside a thermos. Let us know in the comments. This is one of the most fascinating conversations you can possibly have about physics. If you have made it this far, the universe will never look quite the same again when you gaze at the sun on a warm afternoon and feel that heat upon your skin. Share this video with someone you know who has asked that question before, but never found an answer that truly satisfied them, because now you have the complete answer. And subscribe to the channel. Here, the physics of the cosmos is taken seriously, and there is still so much universe left for us to explore together.